So I gave a talk like this about 2 years ago, where I was comparing the, the the modern methods of dose escalation. Um, but at that time, we didn't have a number of those methods actually in fax, and I found doing the comparison rather awkward. Uh, some of the tools to do some of the methods either didn't have a feature I wanted, like some kind of the I3+3 tool didn't have a stopping rule, um, and other tools had a tendency to misbehave, which made using them a little bit tedious. But now they're all in fax, and it's very easy and swift to do the comparisons. And of course, all the results are output in the same way. So I can write one script to extract some values, and it works for all of them. This is the new problem I have in Zoom, which is that when I'm in slideshow like this, simply clicking or doing cursor down doesn't advance the slides anymore. No idea what's going on, so I'll have to present it in this format, to beg your pardon. So what we're not going to look at is the old B+3 or the original Quigley CRM or any of its little variants where just one parameter is estimated. I regard these as having been clearly surpassed by other methods and not worth comparing to. So what we are going to look at are the new rules-based designs that have appeared in the last 15 years or so, called MTPI, I3+3, MTPI2, and BOIN. And also, I'll be comparing them to the updated CRM, the thing we've had in fax for many years now, which based on the work of Beat Neuenschwander, which in fact we called the NCRM. I'm not sure how well that name caught on. So I'm going to variously refer to it as just the CRM or the NCRM or even BLRM, the Bayesian Logistic Regression Model, which is how I think it's referred to in some other places. But if I say CRM, I mean what we used to call the NCRM in fact. If I say the BLRM, I mean the same thing. Now, of course, all these methods had their own papers introducing them. And surprise, surprise, in those papers, when they ran a simulation exercise to show how their method performed, their method always performed better than whatever they were comparing against. So this is an attempt to compare all these 5 methods on hopefully a level playing field. Level certainly in the sense that they're all done in fax. They're all going to be simulated with the same design. And I hope you'll trust me when I say I have not kind of selected features of this design favor any one particular method, and neither did I tinker with the simulation design in order to favor any one method after I started. So this was a prospectively created simulation experiment. So before I get on to the experiment, for the benefit of some people here who may not be familiar with the details of these designs, I am just going to run over them through them as quickly as I can. So these are the key papers. The paper introducing Neuenschwander's changes to the CRM method, as I said, what we called in fact the NCRM. Then there's the paper by Huang on BOIN, by Liu on the I3+3, by Xi on the MTPI, and on Gao on the updated MTPI, the MTPI2. I think if you look at the dates, the first of these was Neuenschwander, 2008. And then MTPI came out in 2013. And then that was followed up by Boyne in 2016, I3 plus 3, the MTPI2 in 2017, and the I3 plus 3 in 2019. And to a certain extent, the Boyne, the I3 plus 3, and the MTPI2 kind of followed on from MTPI and all attempted to be, they're all fairly similar to it, but they attempted to address what was perceived as a problem with it, which we shall see. So looking at the MTPI and the MTPI2, the way the method works is, not surprisingly, you start by defining a target toxicity rate, which we shall call P underscore T. And also, similar to Neuenschwander, they introduce the idea of an interval, of acceptable interval around that rate, or the equivalence interval, EI, where you have some delta, or one or two deltas, which you apply to the target toxicity rate to give you an acceptable lower bound and then an acceptable upper bound. What the MTPI does then is it calculates a beta distribution for each dose where you have data, calculates the beta distribution of the toxicity rate using a standard beta binomial prior. In fact, we use a very non-informative beta binomial prior, with parameters 0.001 and 0.001. Paper seems to suggest that it uses 1,1 as its beta prior, and that seems far too informative to us. In settings where you're looking at having seen one success out of 3, so one success and 2 failures, to have a prior that adds an additional success and an additional failure seems quite strong. What they then do is calculate what they call the unit probability mass of the area below, of the areas below the beta distribution, in the sections or in the ranges below the EI, within the EI, and above the EI. And the unit probability mass is the probability mass of the beta distribution in that area divided by the length of the interval. I think we have a picture to show that. So this picture actually comes from the MTPI2 paper, and you can see here we have some beta distribution. In this case, it's for seeing three toxicities out of 6 observations. We have a target toxicity interval in this that's lying somewhere in the range, something like 0.25 to 0.35. And then within each area, or certainly within this interval and the of the range interval, we have a dashed line that shows what the resulting unit probability mass is, the UPM. And you can see that although the mode is above the interval and a lot of the mass is above the interval, when we scale this mass by the width of the interval, the UPM for the interval is higher than the UPM from above the interval. And what we're going to say is that how the method works is that it takes these UPMs and it says, well, we'll take the region with the highest UPM, the region being below EI below the interval, within the interval and above the interval, and whichever one of those has the highest UPM, we'll use that to base our decision on. If the highest UPM is above the interval, then we de-escalate. If the highest UPM is within the interval, then we stay on the current dose. If the highest UPM is below the interval, then we want to escalate. And this was the problem that was perceived problem with MTPI, which is that in this particular setting, which might be quite a common one, 3 toxicities out of 6, so you've tested 2 cohorts on a dose. The MTPI rule is to stay on that dose. This was regarded as being unacceptable and not attractive to clinicians. And I think it was this instance that gave rise to the separate development of the three other methods, Boeing, I3+3, and then TPI2. So while we're talking about the MTPIs, we'll show you what MTPI2 does, which is that instead of dividing the UPM by the whole interval, so either the target interval or the whole interval or the whole interval above the target interval, it divides the x-axis, as it were, up into equally sized strips, each strip equal to the size of the target interval. And then we separately calculate the UPM in each one. And then we look at the interval, which has the highest UPM. And now, so our target UPM is this one here, MEI. And then there are numerous M highs and M lows. And it turns out in this case that the second M high has the highest UPM. But what you do is you find these new equally sized intervals, which one has the highest UPM, and then you repeat the decision rule we had before. If its UPM is above, if that strip is above the target interval, we de-escalate. If it is the target interval, we stay on the current dose, and if it's below the target interval, we escalate. And then there's a couple of additional fairly obvious rules. So one is that if you're at the highest dose, you can't escalate, so you stay. And if you're at the lowest dose, you stay instead of de-escalating. I mean, that's perhaps interesting that they don't say if you want to de-escalate and there's nowhere to go, you stop. In fact, there's a second rule for stopping, which is that using the probability from the beta binomial, it's the probability that the dose is, the toxicity rate of that dose is above the target rate by some margin, say by 0.95, that's the default, then that dose becomes marked as unacceptable. And not only do you de-escalate from that dose, but you'll never return to it. You're prevented from re-escalating up there. And if that's at the lowest dose, then that's what causes an early stopping of the design. And the last thing is that after the trial stops, and one of the things we include, you can just specify that the trial runs to its maximum sample size. That seems to me unsatisfactory, because if you find the dose early on, it's one of your first couple of doses, then you're just going to sit there running the trial and continuing to allocate to the same dose. So we allow you to specify a cap. And if the dose you are next going to allocate to already has more than this cap on it, then that's what triggers the end of the study. So that's a fairly common rule in the CRM and in other settings. So that seemed like a fairly straightforward thing to add here. But anyway, once your trial, however your trial is finished, the MTD actually isn't just where you were. Before we select the MTD, we perform isotonic regression and use that to take the dose where the post doing the regression, the toxicity is the dose with the toxicity rate that is closest to the target. So we start off with the mean from the beta distribution, which is with a prior 0.005005. So that's simply this. And then the isotonic regression uses the adjacent violators rule, where that if for any dose you've actually got a higher toxicity rate on the lower dose than the higher dose, you simply replace both values by the weighted average of the two sets of data. And the weighting is done using the posterior variance. So we then, from those isotonically transformed means, we simply take the as I said, dose with where the rate is closest to the target toxicity rate. Could be above it, could be below it. And if there is a tie, and of course, if you've done this pooling thing, then you will have adjacent doses with the same value of this transform posterior mean. Then if that mean value is above the target, then you take the lower of the two doses. If that mean value for both is below the target, then you take the higher of the two doses. And I've gone into that in a little bit of detail because the other rules-based methods all do the same thing. So you're going to, so I won't need to repeat that for the other methods. I shall just refer back to they do what MTPI does. So I3 plus 3, how it differs is that instead of using a beta binomial, it simply looks at the, having defined the same thing, a target rate and equivalence interval, it simply looks at the ratio of the number of observed toxicities and the total number of observations. So if X is the number of observed toxicities, then the number of observations at that dose, then we simply look at X over N and whether that's below the lower bound, whether it's within the upper bound or above the upper bound. One small wrinkle of the I3 plus 3 is that if it's above the upper bound, it does one further check, which is it looks at X minus 1 over N. And if that is below the lower bound, then you're allowed to stay at the dose. Otherwise, you de-escalate. And then the same, if you're at the highest dose, you can't escalate. If you're at the lowest dose, you can't de-escalate. And there is the same test for marking doses as being unacceptable. You can't re-escalate to them. And the same isotonic regression after MTPI. Mine starts off the same way, and it's going to use the same decision rules as the I3 plus 3. It uses the same X over N, except it doesn't bother to look at X minus 1 over N if you're above the upper bound. You simply de-escalate. But what it does do is it does modify the boundaries of the interval that you're actually testing against, rather than testing against this target probability minus eta 1 or target probability plus eta 2, which, for the sake of this equation, I've then rechristened P lower and P upper, PL and PU. They've performed a calculation which yields optimal boundaries that minimizes the incorrect escalate, stay, and de-escalate decisions. And those turn out to be calculable in a closed form using this formula. So whatever boundaries you enter into facts for this, or whether you accept what they call the default boundaries, PT times 0.6 and times 1.4, are further transformed into these gammas, no, lambdas. But after that, everything is the same as in I3 plus 3. So you can see these methods are pretty similar, but they do actually yield different sets of decisions and different simulation results, as we'll see. So all of these methods have one attractive feature, which is that ahead of running the trial, given your selections of PT and the interval, and maybe also this threshold, and what we can pre-calculate is that for every combination of number of subjects observed and number of toxicities, we can pre-calculate whether the rules will say escalate, stay, de-escalate, or de-escalate and do not return. So what I'm going to show you now are the decision tables for the four methods for two slightly different settings. One where the target toxicity is 0.3, lower bound 0.25, upper bound 0.35, and another one where the target toxicity is slightly lower, 0.225, with a lower bound of 0.15, and upper bound of 0.3. This last second one is the one we're actually going to use in the simulation example. So here are the decision tables. In each table, you've got across the top, the number of subjects treated at the current dose, and down the side, you've got the number of toxicities observed. So obviously, this is really a sort of upper triangle completed table because you can't have more toxicities than the number of subjects on the current dose. In all designs, if you've seen no toxicities, no matter how many subjects you've observed, we're going to escalate. You can see there are some slight differences for 1 out of 1. Most of them want to de-escalate, except for the I3+3, which would be happy to stay. Now, in practice, of course, as we're going to simulate a trial with cohort size 3, we're only actually interested in 3 of these columns, with 3, 6, or 9 subjects have been observed. So those, for the purpose of this exercise, it's those 3 columns we want to compare. So for 3 subjects, we can see MTPI, MTPI2, and I3+3 are all the same. They're escalate, stay, de-escalate, de-escalate, and do not return. Boyne is different in that it's got no stay. If you test 3 subjects on a dose, you will never stay on that dose. You either escalate or de-escalate. Similarly, by the way, for 6 subjects on a dose, you either escalate or de-escalate. And for 9 subjects, you either escalate or de-escalate. So the Boyne is very, you might say, unstable. It's constantly going up and down the doses. It never retests the dose. The MTPI, you can see by and large, is much more likely to stay. It's got many more stay options than any of the others, including this notorious stay after 3 toxicities after observing 6 subjects. It'll also stay on 9 subjects. It'll also stay if you see 4 toxicities out of 9. It also stays after 2 toxicities out of 9, whereas every other design escalates. The MTPI2 and the I3+3, for columns 3, 6, and 9 have exactly the same behavior. Boyne is, as I said, it's much more bouncy. It's going to go up or down. It doesn't like to stay. And with a slightly reduced, lower toxicity target, MTPI remains much more likely to stay. MTPI and I3+3 remain similar, except after 1 toxicity in a cohort of 3, the MTPI2 will de-escalate, whereas I3+3 will stay. Boyne has slightly more stay options than in the previous example, but most of those are not on columns that we're interested in, but there is a stay at 2 subjects out of 9. And the other remarkable thing about Boyne, though, is it does escalate after 1 out of 6, whereas the others all stay after 1 out of 6, which seems a bit cautious. So there you go. The very similar methods, but they do give rise to just different decision tables. And I guess the question is, does it make any difference in the long run? I'll just quickly reprise the the CRM, the NCRM, the BLRM. Um, there, we don't make decisions based on the data on the last dose tested. We base decisions on all the data and a model fitted to it. We fit a simple Bayesian logistic regression where we estimate the alpha and beta parameters, and we transform the doses to give these what we call the XHATs, the transformed dose strengths. And there are two options, in fact. One is transformation in the Neuschwander paper, log D over a reference dose, or you can simply have the difference between D and a reference dose. In both settings, when the dose, which is the reference dose, should the reference dose actually be a dose in your dose range, then of course the X-hat will be 0 and the logistic will be estimating that dose simply based on the value of alpha. That's the intercept. There is a convention that Neuschwander recommends in his paper, and that some people use, but we've moved away from, which is to use the median of the dose range of the reference dose. Our preference is to use the first dose in the dose range for reasons we don't have time to go into here. So one of the features of this method is, of course, we have to have a prior, an alpha and beta, and it's a bivariate normal. Neuschwander gives a couple of methods for generating the prior, and in fact has actually 4 methods of generating a prior. The two from Neuschwander's paper are all quantiles and quantiles at the highest and lowest dose, which is, in Neuschwander's paper, it's called the uninformative prior. His method of using that has a flaw in it, but actually gives turns out to be a very informative prior with a very constrained values for the slope, and we've modified it. So the prior derivation works differently and doesn't give you these incredibly smooth space of priors where the slope is pretty much the same for everything. We also provide a specific quantiles method, which is kind of like quantiles at highest doses, except you can specify as many doses as you like and which quantile you want to specify. And then there is also the method I prefer and we're going to use here, which is the derived from the scenarios method. So, and the thinking behind the scenarios method is that if in your design you've actually made sure you've got a very comprehensive set of scenarios to simulate, properly representing the range of uncertainty in both where the MTD may lie and also the steepness of the slope or the shallowness of the slope going through that point, then we can simply derive the prior from them. We simply fit the logistic to each one in turn, which gives us a whole set of pairs of alpha and beta. Other than those pairs of alpha and beta, we can then simply derive the bivariate normal. So at any point in the trial, when the results come in from the last cohort, we can fit the BLRM. As you see here, we've got 3 subjects on dose 1 with no toxicity, 3 subjects on dose 3 with no toxicity, 3 subjects on dose 5 with 1 toxicity, and given our prior, the resulting fit has a mean of this solid red line and 95% credible intervals given by the upper and lower dashed lines. And then from that fit, we derive the posterior distribution of toxicity rate at each dose using, and then divide that distribution up into 4 zones, the below toxicity interval, the within toxicity interval, and then the above toxicity interval, which we separate into both excessive and unacceptable toxicity. This split of the above interval is simply to allow 2 different ways of specifying an overdose control constraint. One is to specify it on the whole interval, and the other is to specify it on just the unacceptable. But the next dose to allocate to is selected by simply looking at which dose has the highest probability that its toxicity rate lies in the target toxicity. And then we have a constraint that the probability mass above the target toxicity mustn't exceed some value. So going back to that example, that gives rise to the following posterior probabilities of being under in the target excess or unacceptable toxicity. The under by the blue line, the in the target by the green line, the excess by the orange line, and unacceptable by the red line. So you can see here in this setting, we would next want to redose at dose 5 because that's where the peak of the target is. And that would be dependent on the sum of the excess or unacceptable or the unacceptable being within our overdose control limits. So in our example, we're going to use an overdose control limit on a combination of excess and unacceptable, and it'll be at 0.5. Anything much less than that has a tendency to can cause the escalation to be too cautious. The CRM also allows us to specify escalation rules, which in this case, we're just saying you can only escalate one dose strength. So what we're going to do is we're going to look at two situations which are one is a superset of the other. So one has 6 doses from 25 milligrams to 800 milligrams with the dose doubling. And the other has those 6 doses plus the intervening doses, 37.5, 75, 150, 300, and 600 milligrams. They will all simulate with the same scenarios, but obviously the 11 doses ones has intermediate toxicity values for these intermediate doses. The target DLT rate is 0.225, and our acceptable interval is from 0.15 to 0.3. We create 10 scenarios where there's an MTD at each one of the doses from 37.5 to 800, and there's a mixture of steep and shallow gradients. And these were all created using the FACS different parametric models, only one of which matches the BLRM model for analysis. So they're not sort of favoring the BLRM by all actually turning out to be straight lines in the logit space. All of the designs are going to use cohorts of 3 with a maximum sample size of 45, 15 cohorts for the 6-dose case, and actually 60 and 20 cohorts for the 11-dose case, which I didn't note there in the slide. So this is what the curves look like. I hope you're happy that that's a very varied range, and will probably test the flexibility of all our methods. And these are the actual toxicity values those correspond to, and I've highlighted in red the doses which have toxicity rates which fall within the target interval. And you can see that varies from, in some cases, just a single dose. In other cases, we have as many as 3 doses lying within the interval. In some cases, those doses do occur in the 6-dose case. And in other cases, like this one here, the target toxicity is only achieved by a dose that's present in the 11-dose situation, not in the 6-dose one. The prior derived from these scenarios as these values here, and if we sample from that by very normal 100 times to get 100 pairs of value, alpha and log beta, and then plot the corresponding curves for each of those pairs, they look like this. So you can see how that prior gives rise to a set of curves that does look indeed pretty similar to our population that we're going to be trying to fit. with perhaps a little less likely to fit this extreme case at the end. And jumping straight to the results, so the 1,000 simulations of I3+3 and Boeing, here's a histogram showing for each scenario which how often, or in what proportion of the simulations each dose was selected as the MTD, and then the bars are coloured depending on the true toxicity rate that was simulated for that dose. If the bar's blue, then that dose was below the target interval. If it's green, it was in the target interval. If it was orange, it was above the target interval, but not unacceptable. And if it's red and we don't see any red, then it would have been unacceptable. And the main point to see here is just how similar the performance of the I3+3 and the Boyne is. And indeed, if we go to the MTPI and the MTPI2, once again, the results are extremely similar. So it's going to take a little bit of additional work before we can properly distinguish between these methods, if indeed there is anything to distinguish between these methods. And so, as all four of those are pretty similar, I just picked one set, the I3+3, to compare the CRM to. And you can see the CRM does begin to introduce some differences. It's got a higher peak here in the scenario where the correct choice is a very low dose, and similarly, it does better in the next scenario, although it has a slight higher tendency, if it gets it wrong, to be wrong in the dose above. Things are pretty thin. It does a better job again here, picking the right dose in the when the correct dose is, say, 150 milligram. Pretty similar. And then the other one where, although the peak isn't better, when it gets it wrong, it doesn't. This one, which is a long, flat curve, the models have a tendency, there's a risk that they'll pick a very, very low dose, whereas the CRM has a little bit less of that risk. Interestingly, in the Boeing paper, its advantage over the MTPI is mainly seen when the target toxicity is quite a bit lower than we're simulating. So maybe we aren't in this simulation experiment seeing Boeing at its absolute best. We've got 4 scenarios where the MTD is found better by the CRM than these rules-based ones. But obviously, while they're good for a quick visual scan, those histograms are not very good for a very detailed one. We also want to look at some other properties. So we need to look at, well, how many subjects did the methods enroll? So maybe some took longer and used more cohorts. How many subjects were exposed to toxicity? So what proportion of the subjects tested experienced toxicity? We'll look at the proportion of times that a dose was correctly found and that we had a toxicity rate in the interval. And then, because that's perhaps rather a slightly crude measure, we might want to penalize a design which may have the same ability to choose the MTD, but if it fails, it's more likely to pick too high a dose. We might say that's worse than picking too low a dose. So we've got a 4th score, which is what I've called this loss function, where your penalty for picking a dose in the range is 0, because you got it right, no penalty. Your penalty for picking a dose above the range is the difference between the DLT rate and the upper bound of the range. So you get penalized more the higher you go, the higher that the toxicity rate was above the target. And that's scaled by 200, because we're multiplying 2 probabilities here. So you can think of multiplying it by 2. And then similarly, if you underdose, And so the target, the actual toxicity rate of the selected dose is below the range, then the cost you pay, the loss is the difference, but not twice the difference, by which you're below the lower bound of that target range. Other scoring schemes are possible. So looking at the mean number enrolled, this was quite interesting. The Boolean, so what I've done is show for each scenario, where the name of the scenario is which dose is the true target MTD, and then if there's an F if the curve is shallow or flat, and S if it's steep. The Boolean has a tendency to use, on average, just kind of one more than the mean, one more subject than the mean. So perhaps one out of every 3 simulations, it'll use an extra cohort. And I attribute this to its reluctance to stay on a dose, and it's bouncing up and down the whole time. So when it finds a dose, as it were, it doesn't settle on it. It'll maybe de-escalate, try that one, then re-escalate to it again. So it does have this, I believe, built-in tendency to require, occasionally, or a lot of the time, one more cohort than we might otherwise. Interestingly, the original MTPI has the tendency to be just a little bit quicker than the others. I don't have a reason for that. And then there's just a few of them. The NCRM was the subjects. But that said, all these totals are within 1 or 2 of each other. So the difference isn't actually that big. I suspect that's not a big enough difference to prefer one method over another. The proportion of subjects experiencing toxicity, I've only marked a figure in red if it's the sole model that's been the worst, and I've only marked it in green if it's the sole model that's been the best. And we can see the MTPI2 is actually the best in terms of the subjects within the trial not experiencing toxicity. Now, that doesn't make it the best method, of course. It may just be overly cautious, but it does have a slight cautious tendency. Looking at which method picked the MTD more often, again, it's a bit of a checkered result. There isn't one method that is overwhelmingly and always the best. It does depend on the scenarios. You'll notice we've got 2 scenarios where they all get 0 because the MTD isn't in the 6 doses. And also, there isn't a clear worst. Almost every model is the worst on at least one scenario. Interestingly, MTPI2 is worse more often than the others in terms of selecting the MTD, sometimes not by much, but still that does, on this one though, it's quite a bit worse than any of the others. And that does, I would think, be sufficient and significant enough to, in this setting at least, to mark down the MTPI2 as a model we might be less likely to use. And conversely, the NCRM is the one that takes the MTD more often than the others. Not only does it win in more scenarios than any other, there's a few scenarios where it actually wins by quite a big margin, whereas none of the others do. So the 600 flat, it's got a 45% chance of, oh no, that's not a great significant one, sorry. These first 2 particularly, 77% and 57%, are considerably larger probabilities of picking the MGD than the other methods, which I think probably have a tendency to pick a lower dose a few times. And also the 150 flat, this 50% chance is considerably better than any other method. The other best method is I3+3 with a 40% chance of picking the MTD. So on this shout, I think the NCRM is looking a bit of a favorite. But but is it doing it by overshooting too much? And so we can look at the loss scores, and they're reassuringly, again, the NCRM wins more often than it loses. Interestingly, the two MTPIs do poorly on the loss scores. They're more often the worst, whereas I3+3 and Boyne are rarely the worst or the best. So, in summary, the Boyne is consistently requiring a little bit larger sample size. The MTPI2 consistently experiences fewer toxicities. Um, in the two scenarios where NCRM experiences higher proportions of toxicity, in both those, it's doing considerably better than the other methods in finding the MTD. So it is naturally exploring a dose with a higher toxicity rate. There's no consistently better or worse method at selecting the correct MTD. But the MTPI2 is worse more often than any other method, and NCRM is better, and in three scenarios, significantly better. And there's no consistently better or worse method in terms of loss score, but MTPI and MTPI2 are worse more often than any other method, and NCRM is better more often, and in five scenarios, significantly better. So skipping right ahead to testing 11 doses, we simply repeat what we've done, but now we have all 11 doses present and the simulation scenarios expanded to include the toxicity rates at the intervening value. The other change we make is that we allow NCRM a modified escalation scheme. So it's going to continue to escalate using the 6 doses from the 6-dose regime and only use the interleaving doses when it wants to fall back or it sees some toxicity and it wants to be more cautious moving ahead. There is no scope in the other methods for doing that, and they're going to have to test each of them doses consecutively. And if we look at the I3+3 and the CRM or the NCRM, we do see there's some areas where there's some what looks like significant difference, and other areas where there's a lot of similarity, and one where it looks like I3+3 is doing quite a bit better than the CRM. So again, we resort to numbers to get a detailed handle on this. Once again, the Boyne is requiring a slightly larger sample size, perhaps 2 subjects now. So an extra cohort 2/3 of the time. And the NCRM, particularly where the target MTD is higher up the dose range, is doing considerably better than the others because it's been allowed to skip doses on the way up. This has a penalty for the NCRM, which is the proportion of subjects experiencing toxicity is higher because, of course, it's skipped those lower doses where the toxicity is low. So it's universally more toxicity seen in the NCRM case. And once again, MTPI2 is the lowest, but possibly because it's being overcautious. The selection of MTD again favors the NCRM, and it's now in 7 scenarios. It is now significantly better than the others. And there's one where it's the worst, and there's a couple where either MTPI or I3+3 do better, but not by a lot. MTPI2, interestingly, is now almost universally the worst, or certainly on a lot of the scenarios, except one where it's the best. And on the loss score is a similar tale, where the NCRM is doing considerably better than the others, in some cases by a big margin. Other cases, it's closer. There's just one where it does poorly, the 50 flat. So the Boyne again is consistent, requiring a larger sample size, and the MCR and the NCRM, where the MTD is at a higher dose, is quicker, sometimes significantly so. MTPI2 consistently experiences fewer toxicities, and the NCRM experiences a higher proportion because of its faster escalation. But it's doing a better job at finding the MTD and minimizing the loss score, where the MTPI2 is the worst performer by both measures, and the NCRM is the best, and in many cases, significantly the best. So the last question really is it actually worth in this setting doing the 11 doses? So let's compare the same sets of results, but now let's compare the 6 dose to the 11 dose results. As in order to not have too many numbers, and as the rule-based methods are broadly similar, the MTPIs tend to do worse. So we won't use those. The Boyne has the larger sample size. So what I've picked is the I3+3 and the CRM, and we'll look at how both those do at 6 doses, 11 doses. So you can see, in terms of sample size, not surprisingly, the I3+3, the sample size goes up the higher the MTD is in the 11 dose case. But the NCRM one, it is a bit higher, is not nearly as much higher. That's not really good English, I'm sorry. It doesn't exceed the 6 dose case by as much as the I3+3 does. But there is some cost when the MTD is at the upper range. In terms of experiencing toxicities, these are broadly similar. In the I3+3 with 11 doses, the proportion of toxicity goes down the higher the MTD is up the dose range because we're doing more testing. More of our subjects are being used on low toxicity doses. Whereas the NCRM, although it's with 11 doses, is more has a higher proportion of toxicity than the I3+3, we can see actually all it's doing is mimicking the proportion of toxicity in the 6 dose case because it's using the same escalation. The proportion selection of correct MTD is quite interesting. There are 2 scenarios, the 100 steep and the 400 steep, where there's only one dose that has a toxicity rate that's in our target range, and that dose happens to be present in the 6 dose scenario. And in that setting, the 6 dose design does better in terms of correctly finding the MTD. The 11 dose design, as the additional, or is more likely to mistakenly pick one of these 2 alternate doses, which now just lie just outside the interval. In others, though, the 11 dose scenario does better. Yeah. And all these, and particularly with a couple of them, of course, the MTD doesn't exist at all in the 6 dose case. But there are others where the results are more mixed, and there is no clear advantage to the 11 doses. And this is either where there's quite a few doses, or I think the problem here is that with 11 doses, there is a risk of getting, there is a higher risk picking an MTD below the max or below the true high MTD, because you're testing more doses, and you've got a greater risk that on one of those low doses you get an unlucky number of toxicities. If we look at the loss score, it's a little bit clearer. The loss score is better in the 11 dose case in every scenario except the 2 where there's one true MTD and is present in the 6 doses. So it will depend somewhat on your weighting of the different scenarios, which ones you think are more or less likely. But by and large, the 11 dose, and it will also depend a little bit on the trade-off between the extra precision or the lower loss of the 11 dose versus the slightly longer trial. And with that, I conclude. Thank you very much. Do we have any questions?
No questions from the Q&A. There's still time if you want to type one. Do you want to give us a 30-second, this is what I would do if I had to do dose escalation, your learnings, your weighing all the pros and cons, and your opinion on this?
My preference still remains with the NCRM. It does take a little longer to set up. I do think the problem of choosing the prior is largely solved by using one based on the scenarios and having enough scenarios. I think it's a good idea to have a lot of scenarios, because in a setting like this, you do want to be prepared for the unexpected. And I think if you have access to facts, then the extra complexity of the NCRM is coped for by the fact that you can simply use facts to do the processing during the trial.
Yeah, there's a question basically also asking for the slides. So the recording will be made available. Will the slides themselves be made available to them?
Yes, they will. Let's think how the recordings, we send out a link to the recording pretty much automatically to anyone who's registered for the thing, and then also it'll be moved onto the YouTube channel. I'm just thinking about making the slides available.
Let's make a post on the Knowledge Hub, and we can attach the link to that when we send the recording information out, and then you can follow that link.
Yeah.
Okay, one more question before you go. If you had to narrow this down, if you were to choose only 2 design options that you want to compare for a possible study, which 2 are you pulling out to use?
Much to my surprise, I'm going to say the I3+3 and the NCRM. I was expecting the Boyne to be the most robust of the methods, but I think because I don't like it's bouncing up and down. I'm actually a little bit troubled as to whether it's ethical to test a cohort on 3 subjects at a dose where, irrespective of the results, I know I will de-escalate and test them to dose below it. That troubles me. So I'm a little bit put off the Boyne. The I3+3 is a little bit quicker, as we saw, and has just as good results.
Is the Boyne the only method that can enroll a cohort knowing it's going to de-escalate no matter what?
Good question. I guess we don't need to test the decision tables on some different some other toxicity rates, but you saw that it had a tendency and a strong tendency to have far fewer stay decisions than any of the other methods, and I think that's what gives rise to this.
Yeah. All right. Well, thanks, Tom. Really informative. Lots of in-depth comparison. Might need to go back and watch it again to figure everything out, but it was awesome.
Yes, and apologies for not showing facts at all during this. I kind of assumed that people will be able to look one or the other. If either it's so easy to use, you'll be able to do it, or you can watch some of the other training videos. And or email us if you want the example fax files, and we can send those too.
Awesome. All right. Well,
Okay.
thanks, Tom. Thanks, everyone, for being here. We will see you next time.
Yes, indeed. Thank you very much, everybody. Have a good weekend.